We have been discussing Boltzmann distribution. Where these are relative populations relative to the population of the ground, lowest energy level. G's are the degeneracies of the levels. This expression is a general expression. Let us now apply the Boltzmann expression to a sample of gas molecules. In particular, we will take HCl gas. We are interested in finding the populations of rotational levels the expression for the energy levels are given by the standard expression, rotational constant B times J plus 1, where J takes 0, 1, 2, and so on. Note also that the degeneracy of each rotational energy level is 2 times J plus 1. In this expression, B is the rotational constant. Therefore, we need its numerical value to apply that expression. The rotational constant B for this molecule is this is an experimental value. Okay. Now, as I said, this expression is a general expression. In this notation, we have numbered the energy levels with an integer index starting with 1. So ground state is called 1, number 1, and then the next energy level is 2, the second one is 3, and so on. Now when we apply it to the rotational energy levels case, notice that rotational levels are labeled by the J quantum number, and the lowest value for J is 0. So we need a slight change in our notation so that the lowest level, lowest rotational level is for J equals 0. In that case, energy 0 is 0. Because if J is 0, 0 times anything is 0. This is ground rotational level. And degeneracy of the ground level, the lowest level, for the rotation case, as you see from here, if J is 0, G is 1. In other words, it is non-degenerate. Okay. So this factor, when we apply it to the rotational case, degeneracy of the jth level is given by this expression, 2 times j plus 1. Degeneracy, there is no degeneracy in the ground level. So we have, now I write nj, n sub j divided by n0. Note the change in the index. This is equal to degeneracy of the jth level divided by degeneracy of the ground level. But degeneracy of the ground level for the rotational energies is 1, non-degenerate. So here we have 2 times j plus 1 divided by 1 times exponent e to the minus this term here. That term, when we translate it to our rotational energy symbols, Ej minus E0. This is the lowest level, but E0 is 0. So we have just Ej with this notation. So it is Ej. But what is Ej? It is that expression, B times J plus 1. So it is minus B times J plus 1 divided by KT. Now, we can slightly simplify this expression. You see, populations are changing when J changes. The rotational quantum number J changes. B is a constant. KT is a constant. So we can write this as 2 times j plus 1 times e to the minus a times j plus 1, where a is b divided by kt. Okay. Now, temperature is the room temperature in this example. Temperature is 300 Kelvin. B is, as I indicated there. Then we calculate A. A. Now, if I use SI units for Boltzmann constant, which means joule per Kelvin, then we should also use SI unit. What does it mean? Our data is given in another unit, in wave number unit. So when you use SI units for K, Boltzmann constant and temperature, you must also change B into SI unit. How do you do that? This is energy here. The conversion factor from wave number to joule is H times C. Okay? So if you multiply this with H times C, but you must make sure that for C, you must employ centimeter per second, which means 3 times 10 to the 10, that factor. H is the standard value. Then this expression, this quantity will be expressed in terms of joule. Then you may calculate this. But you may also do it in another way, which is equivalent. Instead of converting B into SI unit, convert K times T into wave number unit. This expression, this calculation, is going to give the KT in which unit? Joule unit, SI unit. All right? Now, if you divide this by HC, you will obtain it in wave number unit. Because how was it? E in joule equals E in wave number unit times H times C. Okay? So, this expression, this number, Boltzmann constant times 300, will give the KT value in joule. But If you want to change it into wave number unit, then as you see from this expression, you divide the value in joule into Hc. This. Then you will get 208.6 wave number. So value of this A is 10.397 wave number divided by 208.6 wave number, and the result is 0.0498. All right. Please note, if you do not divide by H times C, the value will be in joule. You can use that value in the calculation, but in that case, you must convert B into joule also. How do you convert B into joule? Using this expression. B in wave number times Hc will give value of B in joule. You see, H times C is the conversion factor between wave number unit and joule unit. Now, in this expression, everything is fixed now. So we just do the calculation for each value of J quantum number. So if we make a table, this is J, and this is relative population. J values are 0, 1, 2, 3, 8, 9. There is no upper limit for J. So some calculations, for the ground level, by definition, this is 1. Because it is N0 over N0. For J equals 1, calculation gives 2.715. For this, 3.707. For 3, 3.849. Let me include also 4 here. 3.321. For 8, 0.47, and for 9, 0.14. Let us show the energy, rotation energy level diagram. This is J equals 0. Now, this is, I'm just B times J times J plus 1. For J equals 1, this is 2B for j equals 2, 2 times 3 is 6b. The next rotation energy level, j equals 3, 12b. The next one for j 4, 4 times 5, 20, 20b. It's increasing. Degeneracies. Degeneracy is 2j plus 1. So this is non-degenerate. This is triply degenerate. This is 2 times 2 plus 1, 5-fold degenerate. This is 7-fold degenerate. This is 9-fold degenerate, and so on. All right? Now, what we have calculated refer to the following. We have a sample of macroscopic sample of HCl molecules at 300 Kelvin. Now, part of the sample, molecules in part of the sample will be in the lowest rotational energy level. Some others will be in the first excited level. Still others will be in the next excited level, and so on. So there is a distribution in the sample. It's a macroscopic sample, and there are maybe of the order of Avogadro's number of molecules in it, very many molecules. This expression gives number of molecules, say, at this rotation level, divided by number of molecules in the lowest level, relative populations. So, look at this expression. Number of molecules in the first rotational energy level, the energy is 2 times B. Okay? Divided by number of molecules in the ground rotation level is 2.7. What does this mean? If there are 10 molecules in the lowest level, how many molecules are there in the first excited level? 10 times this number, isn't it? 27 molecules will be in the first excited level. All these numbers refer to the populations of the levels, higher levels, relative to the lowest. Okay. Now, this value, which is larger than that one, what is it? 3.7. This is the relative population of the second level relative to the same lowest level. So, what can you say so far? There are more molecules than the lowest level, the ground level, in the first excited rotation level, and the second rotation excited level, which corresponds to j equals 2, has even higher population than the previous ones. You see this value 3.8, and after that numbers are starting to decrease. This is the highest. Highest relative population. And at j equals 3, the relative population is highest. After that, in other words, this level has the highest population. Maximum number of molecules are in this sample at 300 Kelvin are in this level. Populations of all the other levels, either below or above, are smaller than number of molecules in this level. Please remember that because of this exponential Boltzmann factor, as J becomes larger and larger, then A times this factor will be large number, but there is a minus sign here. So all the higher energy populations will be very, very small. Now, let us consider absorption of light by such a sample. We use small, low energy photons. The light we use is in the microwave region. Microwave photons. Then, when a photon is absorbed, a molecule initially in the jth energy level with energy Ej is excited to energy level with J prime. For example, a molecule initially in the lowest level, after absorbing light, can go to either to that level or to that level or to that level. So this means photon energy is delta E, which is Ej prime minus Ej. All right. Now, as far as energy conservation is concerned, there is no restriction between J and J prime quantum numbers, but it turns out that using some other arguments, not every J prime is allowed for a given initial J. Such restrictions are called selection rules. Selection rule in rotational transitions. The change in the rotation quantum number, J, delta J, is restricted to either +1 or -1. So in pure rotational transitions, only J to J plus 1 transitions are allowed. Notice this means delta J is plus 1. In addition, there is a gross selection rule. Only hetero nuclear diatomic molecules absorb microwave photons. Now, what this means is we have many different diatomic molecules, such as, that's a diatomic oxygen molecule, and that's HCl molecule. Now, H2 is homonuclear. According to the gross selection rule, it means that if the sample contains hydrogen gas, it will not absorb microwave radiation. It will be transparent. Microwave radiation will go from this side and it will come out from the other side without being absorbed. Same is true for O2. But for HCl, this is heteronuclear, isn't it? You may also describe this situation as using the word polarity, polar or non-polar. Because homonuclear molecules are also non-polar, right? Whereas heteronuclear molecules are polar molecules. The atoms are different in the molecule. So only polar molecules absorb microwave radiation. That's what it means. Our sample in this example is hydrogen chloride gas. So this gas is going to absorb microwave radiation. But not every transition is possible. Only those transitions which satisfy this restriction are allowed. So what does it mean? The molecules in the ground level can make a transition only to J equals 1 level. So graphically, we can show it like this. The molecules in the J equals 1 level can make a transition to only the next level. Those molecules in J equals 2 level can make a transition to the J equals 3 level, and so on. if you calculate the energy value, energy difference between final level, which is J plus 1 times J plus 2 minus B times J plus 1. If you simplify this, you will obtain 2 times B times J plus 1 for J 0, 1, 2, and so on. Notice that what is the energy difference between the lowest level and the next one? 2b minus 0. The net result is 2b. If you put j equals 0 here, you get 2b. What is the energy difference between this level and that one? 6b minus 2b, 4b. Put j equals 1, 4b. So this is a general expression which gives the energy difference between the one level and the next one. Remember, J is the lower level, lower energy, or initial, because we are talking about absorption. After absorption, energy is going to increase. Energy of the molecule is going to increase. So, photon energy will be delta E. Only those photons whose energies are equal to this delta E, given by this expression, are going to be absorbed. All the other photons with different frequencies are not going to be absorbed. This is in SI units. All right? So, Planck's constant times frequency, the left side, is in SI units. So it must be, of course, such that the right side must also be in SI units. The only quantity that has a unit here is B. B must have joule units to use this. But if you want to use wave number unit for B, then we should make sure that the left side should also have the same unit. That's more convenient because when we use SI units, numbers are very awkward. Like they contain 10 to the minus 19, 20 factors. However, what was B? It was simple, 10 point wave number units. So if you express this in wave number units, what is the conversion factor from joule into wave number? You divide by hc. So we can write frequency or frequency in wave number unit is 2 times B times J plus 1, and B is in wave number unit. Okay? It is the same expression, but the units are different. Light frequency in wave number unit is equal to 2 times B times you may consider this expression, right side, either as frequency of light in wave number unit, and if you want to convert it into hertz, what's the conversion factor? Just C. C times this number, will give it to you in Hertz unit. Or you may regard it as photon energy also. All right? In that case, the conversion factor is H times C. Either way, you may interpret. Okay. Now, we may fill our table. Let's have another. This is frequency of absorbed light in wave number unit. For those molecules that are initially at J equals 0 level, after absorption, they will go into J equals 1 level because of the selection rule. The energy difference is 2B. Those initially in the J equals 1 level will make a transition to J equals 2 level, next level. Energy difference is 6B minus 2B, 4B, or from this expression, put J equals 1 here. So 4 times B, 6 times B, 8 times B, for 4, 10 times B, and you can calculate using this expression or using the energy level diagram. Next energy minus the previous energy type. For 8 plus 1 is 9, 2 times 9 is 18, and this is 20B. So those photons, only those photons, whose with energy either 2B or 4B or 6B or 8B, one of these numbers will be absorbed by the sample. Using our numbers, B is 10.3997. This value is 20.79 wave number. This is 41.59 wave number. This is 6B, 62.38 wave number. And this is 83.18 wave number. All the numbers are given to you. So 10, the next value is 10 times B, which is 103.97. So you can easily complete this table. So the situation is, the experimental setup is like this. We have a source, light source, microwave source. It is the instrument is capable of changing the frequency of the produced light. So it is scanning, changing the frequency and seeing if any absorption takes place, starting from a minimum value to some maximum value within that range. It is continuously changing the microwave frequencies. The results show that only when the frequency is one of these numbers, that one or that one or that one or that one, absorption takes place. At all other frequencies, no absorption. All the light passes through. The sample is transparent to the remaining frequencies. Now, the intensity of absorption is proportional to initial populations. In other words, intensity of this photon with 20.79 wave number frequency depends on how many molecules there are in the lowest level. This value for the photon, absorbed photon, 41.59. This is from J equals 1 to J equals 2 level. Intensity of this transition from J equals 1 to J equals 2 depends on how many molecules are present in the J equals 1 level. Similarly, transition from J equals 2 to J equals 3 level depends on how many molecules there are in J equals 2 level. If there are no molecules in J equals 2 level, is it possible to have an absorption? No. There must be some molecules in the sample at that energy level to cause the to take part in absorption process. So relative intensities of absorption are directly proportional to the initial populations or relative populations. So the relative populations indicate that J equals 1 to J equals 2 level, initial population is this number, relative population, is more intense than J equals 0 to J equals 1 level, because its relative population is 1 for the first transition, this with this energy, 20.79. This is 2.7 times more intense than this transition. The intensity of that from here to here is 2.7 times more intense than from J equals 0 to J equals 1 level. Similarly, this transition from J equals 2 to J equals 3 level, the intensity of this transition is how many? 3.7 times more than this transition. We are comparing always with the same transition. All right? Now we see the highest intensity is from J equals 3 to J equals 4 transition, because the relative population of molecules is highest at J equals 3. All right, we take a break.